Dear friends, today this is the lecture number 4 of current electricity. Today we'll discuss 5 things. First, let's start. Combination of resistor formula. Combination of resistances. Combination of resistances. Resistors. Combination of resistors. You already know this formula in class 10th. Two ways resistors can combine. One is series connection, one is parallel connection. It is very easy for you. So first we'll see series connection. You know this is the symbol of resistor. This is the symbol of resistor. By mistake some students sometimes do like this, but don't do. This is actually the symbol of another device we will discuss later. This is the symbol of inductor. Okay, by mistake some students do like this, don't do. So this is the symbol of resistor. So first we will do series combination. 3 resistors you take. Resistances R1, R2, R3. They now are connected in series. In series combination, what remains constant and what divides? Current remains constant and potential divides. Current remains constant because this is only one way. What current will pass through R1, that current will pass through R2, that current also will pass through R3. So current is same in all the 3 resistors. Because this is series combination. One line is there only, one conductor line. So current will be same. But potential divides. What potential you apply? Suppose you are applying one, this is your cell which provide potential difference V. Then this becomes V1, this becomes V2, this becomes V3. This is the potential difference between the ends of the resistors. V1, V2, V3. But current is same. I current passes through all resistors. Let's write the Ohm's law formula for each resistor. For the first one, V1 is equal to IR1, V2 equal to IR2, V3 equal to IR3. This is the Ohm's law formula for all the 3 resistors. As potential divides here, so we can write net potential V is equal to V1 plus V2 plus V3 because potential divides. Suppose you will give here, you will apply here 100 volt potential. If here it is 10 volt, if here it is 50 volt, you have applied how much volt? 100 volt. If here it is 10, here it is 50, here will be how much? 50 plus 10 is equal to 60. Out of 100, if 60 gone, then how much remain? 40. Total potential divide among all the 3 resistors may not equally because depends on their resistances. If resistances will be same, then the potential differences will be same. Okay, resistances are different, then potential differences will be different. So this is now 50 plus 40, 90 plus 10, 100. This is the total potential difference you have applied. So V is equal to V1 plus V2 plus V3. V is the total potential you have applied. And R is the effective capacitance. If R is the effective capacitance, what formula write here? V equal to IRS. V is the total potential. This is the formula for the total. For the effective. I is the total current. RS is the effective resistances of the 3 resistors, means net resistance. So in place of V, IRS, IR1, IR2, IR3. So now it comes I cancel. RS equal to R1 plus R2 plus R3. It's a very simple one. I have not seen in 15 years this question in the CBSE board examination. It is a very simple question. Everybody know this one just like the kids play. Okay, so it's a very simple one. So this is about the series combination of resistors formula. If the question will be find the effective conductance formula. Effective conductance formula in series combination. Then what is the formula? From here you will start. You will start from here. What will the effective conductance formula? R1 is equal to R1, R is equal to R1 plus R2 plus R3. But if you convert into conductance, I am using the symbol G for conductance. This is 1 by G, this is 1 by G1, this is 1 by G2, this is 1 by G3. The addition of reciprocals. This is the effective conductance formula when the resistors are connected in series. And this is the effective resistance formula in series combination of resistors. Effective resistance formula, effective conductance formula. Okay. If question will ask to derive this one, you have to go only one step more. Remember this one. Sometimes effective conductance, if it will ask then, so you have to go one step more. Then next we go to parallel combination of resistors. It's again another simple one. Parallel combination of resistors. One resistor, another resistor, another resistor. All are connected in parallel. This is the cell connected. This is the potential difference. R1, R2, R3. Cell provides current I. Current always start from the positive terminal. Cell provides current I. This I current divides here. I1, I2, I3. Divides here. This I current divides into three parts. I1, I2, I3. Such that net current I is equal to I1 plus I2 plus I3. So understand this one. So here current divides. But what about the potential difference? That remains same. How? Because terminals of all the three resistors are same. R1 terminal, these two, A and B. R2 terminal, A and B. R3 terminal, A and B. As all the three resistors have same terminal, so potential differences will be obviously same. Because when you will find the potential difference, it will be VA minus VB. VA minus VB per R2. VA minus VB per R3. VA minus VB per R1. So for all the resistors, potential difference will be same. Why in parallel combination potential differences are same? Because all have same terminal. That's the reason why in parallel combination potential differences are same. When you calculate the potential differences as terminals are same, so potential difference will be same. But current divides. Now this current is going in three ways. Okay, so current divides. So now let's write. For this one, write the Ohm's law formula. V, this is V. Potential difference V, here V, here V, totally also V. V is equal to I1 R1. V equal to I2 R2. V equal to I3 R3. And for the net, V equal to I is the total current. This formula I am writing for the total. This is Rp. Effective resistance in parallel combination or net resistance. Okay. So in place of I, now put V by Rp, I1, V by R1 plus V by R2 plus V by R3. If V cancel from both sides, 1 by Rp equal to 1 by R1 plus R2 plus R3. This is the effective resistance formula in which combination? Parallel combination. So next come to what is the effective conductance formula? What will we follow? Effective conductance formula, from this we find 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. So in place of 1 by Rp I will write now this is Gp. Gp, reciprocal of resistance, is called conductance. This is G1, this is G2, this is G3. Effective conductance formula. This is for parallel combination of resistors. For parallel combination of resistors, this is the effective resistance formula, this is the effective conductance formula, just the reverse. just the reverse. Okay, what is the resistance formula in series combination? That is just like the same formula for effective conductance in parallel combination. Okay, so just the reverse. So this is the effective resistance and effective conductance formula in both the series combination and parallel combination. And one thing I want to tell you here, you can use this shortcut one. Suppose two resistors are connected in parallel, 1 by R1 plus 1 by R2. This is 1 by Rp. So if you take LCM, R1 R2, here R1 plus R2. So what is Rp now? Total resistance R1 R2 by R1 plus R2. Okay, I need Rp. I don't need 1 by Rp. I need Rp. Okay, total resistance in parallel combination. This is R1 R2 by R1 plus R2. You can remember this is shortcut one to find the effective resistance in parallel combination. I will show you one example here. You see, 2 ohm. This is 3 ohm. Both are connected in parallel. Find the effective resistance formula. In this, okay, if I tell you to find effective resistance formula, then what is 1 by R? 1 by R is equal to, we will write the formula 1 by 2 plus 1 by 3. Then this is take LCM 6. Then this is 3 plus 2. So the answer is coming 5 by 6 ohm. The answer is coming how much? This is 2 ohm. This is 3 ohm. The answer is coming now. This 3 plus 2 5. This is 5 by 6 ohm. So what is the effective resistance here? 5 by 6 ohm. Right? Okay, you are thinking now sir is doing one mistake. What mistake I am doing? I did the calculation, but I need the effective resistance in this side, in LHS side. This is 1 by R. So what will be my answer? My answer will be R. R is equal to 6 by 5 ohm. Answer will be 6 by 5 ohm. But just before I stop here telling 5 by 6 ohm. Not I. Many students do like this. Just I show you this one. The many students do like this. While calculating parallel, this is a common mistake. I always tell you the common mistakes. This is a common mistake. While calculating the parallel combination, intention in exam or when they do the answer hurriedly, then what happens? They forget to just reverse it to get R. They sometimes stop here and tell the answer or write the answer 5 by 6 ohm. Okay, so to avoid this type of problem, you can use this formula directly. See how this formula directly works here. R1 R2. So 3 into 2. R1 R2 by R1 plus R2. So 6 by 5 ohm. Directly you got the answer. This one will be little easy for you to find the effective resistance in parallel combination. Then about circuits I will solve in next videos about these circuits, different combination of resistors. So this is about the formula for combination of resistors in series and in parallel combination. Next we will go to ohmic and non-ohmic device. Let's see, ohmic and non-ohmic device. What do you mean by substance? Ohmic and non-ohmic substance. Substances are classified in two types based on Ohm's law. Based on Ohm's law, the substances are classified into two types. One is ohmic, one is non-ohmic. So first we discuss about ohmic. What is ohmic? Very simple. The substance which obeys Ohm's law. The substance which obeys Ohm's law is called as ohmic substance. Obeys Ohm's law means V proportional to I. Then how will the graph? Graph will be like this. For the substances obey Ohm's law, graph will be like this. This is the graph. V, this is I. Or you can take here also I, you can take here V, no problem. Only the slope will change. So V and I. So this is the ohmic substance. The substance which obeys Ohm's law is called as ohmic substance. This is the graph of ohmic substance. BA graph will be a straight line. The question may come to your mind, practically what is the ohmic substance? Please tell us. Practically where it is available. Which substance in your day-to-day life is called ohmic substance? Conductors, metals. Metals carrying low current. Metals carrying low current are ohmic substances. Metals carrying low current, I told you. Example of ohmic substance, if you will ask me, then this is metal carrying low current. I told you low current. It's called this is the example of ohmic substance. Then the question may come to your mind, why I am using the word low current? This is a 2020 board exam question. 2020 board exam question. This is very conceptual question. The question comes from the word. One word. This is the answer. This word, only these two words. Metals carrying low current. These two words are important. Why carrying low current is ohmic? If the current will be high, is there any problem? Is there anything happen if the current will be high? Yes. If the current will be high, what happens? Due to high current, the metal gets heated. We'll discuss at the end of this chapter about thermal effect. Also, you know in lower classes when current passes through a conductor, the conductor gets heated. When the conductor gets heated, its temperature will be constant or not? Temperature will not be constant. If temperature is not constant, Ohm's law will be valid or not? Ohm's law will not valid. If current will be high, metal gets heated, temperature increases, Ohm's law will not valid. So it will not obey Ohm's law. It will not obey Ohm's law. If it's metal, its resistance increases. Resistance will be no more constant. In Ohm's law, resistance has to be constant. But if temperature increases, resistance will be no more constant. Resistance will increase. How it will increase, we will discuss just after some time. So when temperature increases, its resistance increases. So it doesn't obey Ohm's law. Now you see, if this is the normal graph, but if temperature increases, what will happen? If temperature increases, this should be the graph. This is the graph, it should be a straight line. Okay, it should be a straight line. Clear? Like this, the straight line. Up to low currents. But when current becomes high, more and more current will apply. Then how this graph will go? This graph should go like this, but now what happens to the graph? If current becomes high, the graph will turn like this. The graph will deviate from its straight line path. Will bend like this. This graph will bend like this, you see. It will deviate from its straight line path. The graph will bend. It will not now go through this straight line. The question again may come in exam. You understand one concept? Ohmic substance means metal carrying low current. The question will come, why at a high current the graph deviates from straight line in Ohm's law? At high current, why the graph deviates from straight line? Why deviates from straight line? I told you already. At high current, temperature current increases, metal get heated, temperature increases. I am writing here, you will understand better. So at high current, current increases. If current increases, then metal gets heated. If metal gets heated, then what increases? Temperature increases. If temperature increases, then what happens? Resistance increases. So the graph deviates from the straight line. If deviates from straight line, why it is going up? Why not going down like this? Sometimes some students confused. It is towards up or towards down. It's very simple. Very simple. If this is VA graph, you are taking V in this axis. Now you see what happened. So if temperature increases, then resistance increases. If resistance increases, the graph has to be bent like this. Why? Because slope has to increase. Slope is equal to resistance. If resistance increases, then slope increases. I am writing any more steps. See, slope increases. Slope increases means theta increases. You see, here is the theta, but here it will calculate. Here we will find the slope. How the graph will be? How the tangent will be? Tangent will be like this. See, this will be the theta. This is theta 1, this is theta 2. Which theta is more? Theta 2 greater than theta 1. Theta 2 is greater than theta 1. So more theta, more slope, more resistance. So resistance increases. As increase, so the graph will bend towards the up. Now you are clear about this. What questions you expect here? So what is the example of ohmic substance? Metal carrying low current. Metal carrying high current are not ohmic substance, because current high, metal gets heated, temperature high, resistance is no more constant, so Ohm's law is violated. Then the question may come, why the graph deviates from straight line at high current in Ohm's law? I told you, because current increases, temperature increases, resistance increases, slope increases, then the graph bent from the straight line. So this is about ohmic substance, the substance which obey Ohm's law. This is the ohmic substance. Then the next one will go to non-ohmic substance. What is non-ohmic substance? Very simple, the substance which doesn't obey Ohm's law. The substance which doesn't obey Ohm's law is non-ohmic substance. Its graph will never a straight line. Graph will not be a straight line. VI graph, if you see in this non-ohmic substance, the graph will not be straight line. The graph will be of a different shape. Different shape. So you are expecting some examples of non-ohmic substance? Yes, examples of non-ohmic substance. I am writing, you see, your semiconductor diode. Semiconductor diode. You will read this one at the end of the book. Last chapter, semiconductor diode. It's not obey Ohm's law. Then dilute H2SO4. This not obey Ohm's law. Then water voltmeter. Water voltmeter. This also not obey Ohm's law. Then thyristor. Thyristor is a device. It also not obey Ohm's law. Thyristor. Okay. Thyristor, water voltmeter, semiconductor diode, all these devices, all these substances, they do not obey Ohm's law. These are the non-ohmic substances. Are you expecting the graph? As you are expecting, I will draw the graph for this. How the graph, if the graph is not straight line, how the graph looks like for these substances. But I will not fulfill your wish. So this graph you will search the books. I am just giving you this question to make you to search the book, because I know you have not opened the book since 2 months or 3 months. Okay, so now you will open the book. You will search where the graphs in different books. These graphs will be available, may not in one book. Okay, so you will draw the graph for these substances. This is the homework for you. So this is about non-ohmic substance. But one question I want to ask you, very rare question you will find in very rare books. This is also up to you. Which electrolyte is ohmic? Again I am repeating this question. Which electrolyte is ohmic? Okay, means obeys Ohm's law. This question is up to you. So this is about ohmic and non-ohmic substance. Next we go to variation of resistivity with temperature. We know in resistivity formula, M by N E square tau. M constant, N constant for a material, E constant, tau depends on temperature. Due to this, tau resistivity varies with temperature. So we have to discuss how resistivity varies with temperature. Variation of resistivity with the temperature. What is the expression? rho T equal to rho naught whole into 1 plus alpha T. Variation of resistivity with temperature. Rho T equal to rho naught whole into 1 plus alpha T. This is the direct formula I am giving to you. Resistivity varies with temperature according to this formula. Okay. So what is rho T? Rho T is the resistivity at T degree Celsius. T degree Celsius. Rho naught is the resistivity at 0 degree Celsius. And alpha is a constant called as temperature coefficient of resistivity. Alpha is called as temperature coefficient of resistivity. Then what is T? T is the increase in temperature. T is the change in temperature. Also you can tell in this formula, rho T is the final resistivity. This is the initial resistivity. You can use as initial resistivity, whatever you have, at which temperature you may take, doesn't matter. This is the initial resistivity, it was. This is the final resistivity, now it is. And alpha is constant, I told you. T is the change in temperature. Final temperature minus initial temperature. But this formula is same, but action is different according to the substances. We know our substances are classified in 3 types: conductor, semiconductor, insulator. Conductor, semiconductor, insulator. So let's first discuss about conductor. Okay, before discussing conductor, let's do one thing. Let's find the definition of alpha. This is a constant temperature coefficient of resistivity I told you. Let's find the definition of alpha. What is the alpha definition? Rho T. This is rho naught plus rho naught alpha T. Then alpha equal to rho T minus rho naught by rho naught T. This is the formula of alpha. Okay. Then what will be the definition of alpha? It comes in the board examination. Definition of alpha. Definition of temperature coefficient of resistivity. Mathematical definition, right? Temperature coefficient of resistivity of a material is defined as change in resistivity for original resistivity for unit rise in temperature or unit change in temperature. Again I am repeating you. Coefficient of temperature coefficient of resistivity for a particular material is defined as change in resistivity for original resistivity, for unit rise in temperature. Okay, so this is the definition of temperature coefficient of resistivity. If it come in exam, then you can able to write what is this SI unit. It many times comes in the board examination as well as in school examinations. What is the definition? What is the unit SI unit of this temperature coefficient of resistivity? What is the SI unit of temperature coefficient of resistivity? It always comes in the board examination. SI unit of this. You see, these two units with this unit will be cancelled. Okay, these two units with this it will be cancelled. Okay, so this is the resistivity unit and resistivity unit. They will cancel. What only remain? Temperature. What is the SI unit of temperature? What is the SI unit of temperature? Kelvin. So the SI unit is Kelvin inverse. Remember, very important. The SI unit of temperature coefficient of resistivity is Kelvin inverse. So now we will come to the different type of the materials. First discuss about conductor. What happens in conductor? Conductor alpha is positive. Conductor alpha is positive. If alpha is positive, this term will be added with rho naught. So which will be greater, rho T or rho naught? You see. So it is very clear rho T will be more than rho naught. Rho T will be more than rho naught if alpha is positive. So when temperature increases, resistivity also increases. In resistor, when temperature increases, resistivity also increases. Okay? The question may come to your mind, certain tell us the electronic theory. Actually, why this happens? When temperature increases in conductor, why resistivity increases? Resistivity increases means obviously resistance increases. But why? Why the resistance increases with increase in temperature? Because if we go to the electronic theory, then what happens? In two ways I can explain you the answer. So what happens there? When temperature increases, kinetic energy of the electrons increases. Velocity of the electrons increases. If it increases, if velocity will increase, what about the number of collisions? Number of collisions will be more. Number of collisions will be more. If number of collisions will be more, then what happens to the resistivity? Resistance. What happens to the resistivity? Increases. Again, I am telling you, if temperature increases, then resistivity of a conductor increases. So, why increases? What is the reason behind it? I am telling you the reason. If temperature increases, then kinetic energy of the electrons increases. Means their velocity increases. If velocity increases, number of collisions per second, this increases. Number of collisions per second increases. Okay. If number of collisions per second increases, then resistivity increases. Is it clear now? More number of collisions will happen. You imagine, suppose now on the road, all the vehicle speed will make a triple. The vehicle someone is driving with 40 km per hour, that person will start driving with 120 km per hour. All vehicles speed you make a triple, not triple, you make double. What happens to the number of collisions? What happens to the number of collisions? Immediately number of collisions will increase. Immediately number of accidents will increase if the velocity will be triple or double. So the number of collisions per second increases, hence the resistivity increases. I can also explain you it another way. M by N E square tau. Mathematically I am also explaining you this answer. If temperature increases, what happens? What happens if temperature increases? This tau. See, which one will be affected? Tau. This tau decreases. I had told you earlier, temperature tau are inversely related. If tau decreases, what about rho increases? Temperature increases, the resistivity increases. Mathematically also we can explain it. In two ways we can explain it. Anyone you can write in exam. Don't confuse that which one will write in exams. I am explaining two methods to write. Any one method you can write, no problem, you will get full mark. So this is about conductor. Now come to semiconductor. In conductor I am giving you another homework. I am giving you one homework in conductor. You have to draw the resistivity versus temperature graph for copper and nichrome. For copper and nichrome, you have to draw resistivity versus temperature graph. This question many times comes in exam. Many times this question comes in exam to draw. This is a remembering type question. Okay, so remembering type question to draw the graph. Draw the graph. It's a remembering type question. So copper and for nichrome. Then let's come to the semiconductor. What happens in semiconductor? Alpha is negative. Semiconductor alpha is negative. Okay, if alpha is negative, then what happens? Rho t will be less than rho naught. This term will be minus. If one term will be minus from rho naught, then it will decrease. Rho t will be less than rho naught. But with increase in temperature, resistivity decreases in semiconductor. If you draw the graph, it's a very important graph. It's a very important graph. Resistivity versus temperature graph. The graph is inversely proportional graph. Graph will be like this. If temperature increases, resistivity decreases. It's a very important graph. Always comes in exam. The draw resistivity versus temperature graph for semiconductor. Okay, temperature increase, resistivity decrease. But one thing I want to share with you, very interesting thing here. This graph always comes in exam, draw resistivity versus temperature graph for semiconductor. But once in exam the question comes, draw resistivity versus temperature graph for germanium. Now matter closed. Resistivity versus temperature graph for germanium. What happened? After exam, some students, after coming out of the exam hall, they told, sir, we don't know resistivity versus temperature graph for germanium. Sir, we know resistivity versus temperature graph for semiconductor. But sir, where is the graph for germanium? It is not, sir, in book. Dear students, germanium is a semiconductor. I told them germanium is a semiconductor. It's not required to tell. Semiconductor, for semiconductor means that is also for germanium. Okay, you are thinking, sir, we also don't know germanium is a semiconductor. But actually semiconductor is a chapter of your syllabus in the last chapter of your book. In that chapter you know the name of many semiconductors. And after that you will appear the exam. Don't worry. You will know the name of many. After knowing that one also students are getting confused. Some having very good brains. Okay. So resistivity versus temperature graph for semiconductor means if an example will give resistivity versus temperature graph for germanium will draw. The same graph you will draw. Don't be confused about this. Okay. So but the question comes of why? Why with increase in temperature resistivity decreases? Why this happens? So let's come to the points. Now resistivity formula, N by N is square tau. N by N is equal to tau. Okay, now let's discuss from this one. If temperature increase, then what happens? Here this one, what is this? This is charge carrier density. In semiconductor also these charge carriers are available. There are two types of charge carriers there in semiconductor, free electrons and holes. One type of charge carrier will be discussed in the last chapter. Don't worry about that, but you just refer here free electrons and holes, another type of charge carrier. Okay, are there. When temperature increases, this N increases. Number of charge carriers initially in semiconductor charge carriers are very less. Hence its name is semiconductor, not conductor. Semiconductor, because charge carriers are less. But when temperature increases, number of charge carriers increases. If number of charge carriers increases, what about rho? Rho decreases. Temperature increase or resistivity decrease. Semiconductor conducts easily, conducts very good if temperature will increase. Temperature increases, then resistivity decreases. You could able to understand this formula. Rho is equal to N by N is equal to tau. When temperature increases, more and more charge carriers will be available there. They will come out of the atom with increasing temperature. Initially charge carriers are very less. When N increases with very large value, then rho decreases. Means resistivity decreases, it conducts easily. In semiconductor this happens. Both are inversely related. You see one arrow is up, one arrow is down. They are inversely related. Now some are thinking. Sir is doing cheating. What? In which way? Tau I am sitting here. Can you able to catch? In which way I am sitting here? While discussing about conductor. See, I told you temperature increase, tau decrease. This is while discussing about conductor. This is while discussing about semiconductor. Okay, tau decrease, so rho increase. So now the question, you see the both side comparison, in which I am now checking you. Temperature increase, I told temperature increase, so tau decrease. I didn't tell about this N. Then you could able to understand. But when this comes, Temperature increase, I told N increases, but I am not telling about this tau. I am not telling about this tau. Then you can also understand. But I am telling you actually what happened. I am not sitting you. You see, this is also one important question. I am telling you about this. In conductor, this N is very large. Large number of charge carriers there in conductor. Large. I have told you one calculation. 10 to the power 29. 10 to the power 29 per meter cube. Free electrons are available in a conductor. When temperature increase, actually both gets affected. N gets affected, tau gets affected. But as number of electrons are very large, due to increase in temperature, some electrons may generate, but their number will be very. Suppose electrons generate how many? Suppose 10 electrons generates. I am just giving one example, not exact calculation. Suppose 10 electrons generate. Is there any much effect? Is there any much effect on this? Near 10 to the power 29, what is the value of 10? So N, though change, but its change is not significant. Its change is not that much value so that we will calculate it, we will consider it. But this change in tau will affect. Because large number of electrons are there, all start moving very quickly, collision happens immediately. Okay, this gets affected. So, when temperature increases, both gates change, but this change is very less. So, tau dominates the effect of N. And almost no change in N. But what about this? In this, initially this N is very less. Suppose I am telling 10. Few charge carriers are there in the semiconductor. Its name is semiconductor, I told you. Few. But due to increase in temperature, more. Suppose 10, the same 10 if it will be added here due to increase in temperature. This is added due to increase in temperature. You see the number becomes double. Number becomes double. So here this change is significant. This change is more. But what about tau? Tau effect is dominated. What collision? Free electrons are not there. What collision will happen? What speed will increase? No more electrons are not there. In a large volume, few charge carriers are there. But here in a small volume, more charge carriers are there. Crowded, traffic is more here, more traffic. But here, speed may increase. What about the collision? Because electrons are not there, that much electrons are not there. With very less traffic, speed may increase. But collision may not happen. Okay, that amount of collision will not happen. So remember this one. Remember here. So in semiconductor, when temperature increases, number of charge carrier density increases, which dominate the effect of tau. So resistivity decreases. Remember this one. I am not checking you. I explain this one. Understand? Okay. So this is about the variation of resistivity in semiconductor. The graph is very important, I told you. Then insulator, nothing to discuss in insulator. Okay, it's a bad conductor, insulator. So always you neglect that one. If temperature increase also in insulator, alpha is negative. Temperature coefficient is also negative. Because very few electrons will be available. But still they will be unable to conduct electricity easily. So insulator, you remember, insulator means we are telling it's poor conductor. We are telling the insulator in lower classes also you are using poor conductor. Insulator, poor conductor. Okay, otherwise insulator will feel bad. So we are using the word conductor. But back to it, poor. Poor conductor. Okay, so insulator is also a poor conductor. It conducts, but very less it conducts. If temperature will increase, very few electrons will. So nothing to discuss in insulator. Alpha is negative. So when temperature increases, also resistivity decreases in insulator. This much only you know. So this is about the temperature variation of resistivity with temperature. Also you can write the same formula in resistance also. RT equal to R naught whole into 1 plus alpha. You can write in resistance form way, no problem. Then the alpha is called as temperature coefficient of resistance. An explanation everything is same. Temperature coefficient of resistance. Don't worry about this. Don't be confused. In some books you may write in form of resistance. I'll go to the fourth part. Then that is superconductivity is a very important one. Superconductivity. What is this? Just before I told you, in a substance, suppose in a conductor, if temperature increase, then resistivity increase. If temperature decrease, then resistivity decrease. Decrease, then resistivity decrease. Now you come to this point. In a substance, when temperature decrease, resistivity decrease. Resistivity decrease. How much it will decrease? Decrease again. Decreasing, coming towards low value. Now 100, 80, 70, 50, 40, 30, 20. Decrease, becomes 0. Resistivity becomes 0. Is it possible? Resistivity, temperature will decrease and the resistivity decrease and will become 0. Resistivity becomes 0. I am not telling you this one. This is not a story. This happened when? In 1911. In 1911, this phenomenon came in physics for first time in 1911. The name of the scientist, one Dutch scientist, Kamerlingh-Onnes. Kamerlingh-Onnes, one scientist, while doing the experiment in his laboratory, checking mercury. In mercury he found. In mercury what he did? He decreased the temperature, and found at a particular temperature, resistivity becomes 0. At which temperature? At temperature 4.2 Kelvin. He became happy when he saw resistivity become 0. Resistivity 0 means what? No opposition. Current will pass easily. Imagine now, current will pass easily. No opposition, no loss of current. Nothing will happen. It's very good. If no opposition, nothing, conductor will not heat in the way. While passing the current, conductor will not heat. No loss will happen. Kamerlingh-Onnes become very happy when resistivity is 0. It's not a conductor. What is this? Superconductor. Then the phenomenon comes superconductivity. Superconductivity, the phenomenon. What is superconductivity? It's the situation when the resistivity of a substance is 0. Then the substance is treated as a superconductor, and the phenomenon is called superconductivity. When the resistivity of a substance becomes 0, then it is called, the substance is called superconductor, not conductor, superconductor, and the phenomenon is called superconductivity. Kamerlingh-Onnes found this in his laboratory in 1911, but Kamerlingh-Onnes became unhappy when saw the temperature. At 4.2 Kelvin resistivity is becoming 0. How will I achieve 4.2 Kelvin? How will I achieve 4.2 Kelvin? It's a very small temperature. 0 Kelvin. You know molecular motion suggests. Molecular motion sees at 0 Kelvin. 4.2 Kelvin. How will I achieve it? Is it possible? No, it's not possible. In our practical life, day-to-day life, it's not possible. Okay, it may not possible in our practical, may not possible at that time. But our scientists then did a lot of research, and now superconductor we are getting even if at room temperature. Research is going on about this, and we are getting superconductor even if at room temperature we are getting the superconductor, and they are in use. You may ask the questions at where it is used. Superconductor, where it is used? We have not seen any superconductor. You are using the superconductor. Many data you are storing in your laptop, in your desktop, where you are storing a large amount of data. Where you are storing? Pen drive? No. Compact disk? No. Your Google Drive? No. Where you are storing? Hard disks. Your hard disk, superconductivity. superconductivity, but that in your hard disk, that is a superconducting material. Okay, so superconductor are now in use. And another thing also I am telling you, this temperature, critical temperature, this temperature is called as critical temperature. The temperature below which resistivity becomes 0 is called as a critical temperature. And what is superconductor? You know, this once came in the board examination just before 1 year. In the board exam, this came. When the resistivity of a substance becomes 0, the phenomenon is called as what? Like this, the question came. What is this? What is this called? What is this called? Superconductivity, or the substance is called superconductor. Okay, so this is about the superconductor, and who found your that superconducting material about the hard disk superconductivity also got the Nobel Prize some years back about that. So this is about the superconductor graph. The graph comes in exam. In the board examination, this question was in the board examination. This is Tc. This is T, temperature. This is resistivity. This is 4 Kelvin for mercury. Tamberlin was got. Okay. So this is Tc. Resistivity decrease. Suddenly becomes 0 at 4.2 Kelvin for mercury. If the graph will ask for resistivity, temperature graph for superconductor, you will draw this graph. Okay, so this is about the superconductor. The last part now I will discuss is the color code of carbon resistors. Have you seen resistors in market? You may not see. I will show you to the resistor how it looks like, about what you are reading. You have already read in class 10th, but I think you have not seen the resistor. So I will show you that one. But when you see the resistor, how will you find this resistance? How will you find this? I am telling one incident to you. Once I was in the market in an electronic shop in Bapuji Nagar. I was there. What happened? One person came and asked, I want some resistors. Then the boy who was the sweeper there in the shop, immediately asked, how much ohm? How much ohm you need? The person told, I need a resistor of 50 ohm. Then the boy immediately went and brought one resistor packet. Okay, and they gave the person, this is the 50 ohm. Okay, then the person took the resistor and went away from the shop. But I was watching all these things at that time. Then I know already how I will calculate the resistance of the resistor. But then in curiosity I went to that boy and I asked him that how you know that this resistor has a resistance of 50 ohm. Then he immediately told me, he immediately explained everything to me. He taught me the physics there. He showed me the resistor, about all the colors are there, I tell you now, but all the colors, and he explained me how to calculate the resistance. I got astonished that he knows everything, how to calculate the resistance of the resistor. Then I was very much impressed on that day. Then I thought if he will appear the exam, he will must get 1 mark in the board examination. Okay, you people may not get, but he will get 1 mark in the board examination, finding the resistance of carbon resistor. Okay, so now see how your carbon resistor looks like. It looks like this. This is the resistor. It has 4 color bands. 1 color band, 2, 3. I am showing you this part. 4 color band resistor I am showing you. This is in your book, but many structures are there, but I am showing this one. First color, second color, third color. Last one is called tolerance. Resistors are looking like this. Okay, last color is tolerance. All these colors are the codes. First let me tell you the codes, then we will go to the resistor. Codes. What codes here? Codes now. I am writing the codes. Remember the codes, there is a shortcut way. You may know that one. Still I am telling you. B.B. Roy of Great Britain had a very good wife wearing gold and silver necklace. Okay, B.B. Roy of Great Britain had a very good wife wearing gold and silver necklace. You will now see this one. We will also write this. B.B. Roy of Great Britain had a very good wife wearing gold and silver necklace. B for black, B for brown, red, orange, yellow, green, blue, violet, grey. Green first comes, then grey. Okay, don't confuse what is easy. Also B, two B's are there. First is brown, second is blue, then this is white. Okay, white is white, then gold. These three are called tolerance. These three are the fourth color. In the fourth color only these three will find in the fourth band. Okay, this they are called tolerance. Tolerance, I am telling you what is tolerance. Gold, this gold is gold, silver is silver, and this one is no color. Necklace means no color. Its value is tolerance is 5%, 10%, 20%. The tolerance, whatever may the resistance value, plus or minus this much will write. Means this will debit plus this much percent or minus this much percent. Okay, those values fluctuate. For black code is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if you got the codes now, okay. So how will you find the resistance of this resistor? Now let's see. Suppose this color is, I am writing the colors. Suppose this color is red, this color is suppose yellow, this color is suppose let's take this as orange. Okay, and the last one is suppose take silver. What is the resistance of this? How will you find the resistance? Okay, what you do? First color is red. Mark this one, red. Red, you see red. Where is red? Red is 2. Write 2. Second color is yellow. Yellow code is 4. Write 4. Third color is orange. 3. Write 3. No. Third color you will not write this. You will not write like this. Don't do the mistake. You will write this into 10 to the power 3. Third color will write into 10, whatever the third color is there, into 10 to the power you will raise the power. Remember, third color. Then plus or minus, this is silver, silver is 10%, tolerance is 10%. Understand? Okay, so this is the resistance ohm. This is the resistance of the carbon resistor. In this way, you can find the resistance of carbon resistor. Just I am telling you, I am showing you, see one resistor. I am showing you, you see this resistor. Okay, you see this one. You can able to see this one now. See this resistor. Okay, so what is the first color? See the first color. First color is, that is the brown. Okay, you see one is written there. Okay, then what is the second color? Second color is red. For red, what is the code? 2. For red, code is 2. Okay, the third color is, you see the third color, the code is 5. Third color is, that is a green. So 10 to the power 5. See, first brown 1, red 2. Then the third color will be 10 to the power. The tolerance is gold. Gold means plus or minus 5%. Okay, so this is the resistor. Resistor looks like this. Okay, also I will show you practically how the resistor looks like. I am showing you the resistor. I have a circuit. You can also see. So see, this is the circuit I am showing you. Okay, this is a very small one. You can able to see. See the circuits. Many resistors are there. Can you mark? See that like this the color. Many resistors are there. This one I am showing you also. This is called. This is a capacitor. You see. This is a capacitor. Okay. This is one capacitor. This is one transformer. This red one transformer. This is LED. You all have seen. This is LED. Okay. This is also one capacitor. Okay. This smaller. See this small. This small. This one capacitor. This one. Okay. And resistors. You see one resistor here. one big resistor you see. This is the big resistor. Okay, this is the big one. Okay, this one is the big resistor. Okay, I am also showing you another resistor. You see, another resistor. See, this is the resistor. If it is visible to you, you can see this is the. I show you this one. In this, many resistors are there. Many resistors are there. Okay, another resistor also I am showing you, very small one. You see, this is the resistor. It may not be visible, it's a very small one, but you see the resistors you saw that how you find the resistances you can buy from the market. It's a very small cost resistors you can able to buy, and you can find the resistances. So today we'll discuss a lot of things, 5 things we discussed, and we finished almost 50% of the current electricity chapter. But easy portion is over. From the next lecture, the important and difficult portions will come. Thank you.